Hello, right, we've got a few more circuit questions. We're starting here with an IV characteristic of an LED. So LEDs, remember, you're going to have small currents, and as we see here, we've got milliamps, so don't make the mistake of leaving that out. Always check your y-axis. Use figure 2.2 to state the value of the resistance below 1.4 volts. It's interesting they've said state on that one. I mean, you can do the calculation because, of course, we've got R is V over I. I know this is non-ohmic, as in the resistance is changing because it's not a straight line. Remember, that's the point of Ohm's law. But we can still use this relationship. State this. I mean, if we were going to calculate it, we'll be saying, well, whatever voltage we pick, we're dividing by 0 because we've got no current. So we're getting infinite resistance. We can then use this again where it says then determine the resistance R. That V is 1.8 volts. So we're going to have 1.8 divided by whatever the current is at 1.8 volts, which is what here, that's 10 milliamps, 0.01. That's 100 times 1.8, which is 180 ohms. So we got 180 ohms there. So a couple of quick calculations. At voltages V above 1.8 volts, state whether the resistance of the LED increases, remains the same, or decreases as V increases. Justify your answer, right? Sometimes people get caught out with this because they're so busy thinking of ohmic conductors that they're looking at the gradient, then saying, oh yeah, well the gradient hasn't changed. But that isn't what's mattering here because it's non-ohmic. We are seeing that I is increasing a lot quicker than the voltage, faster than V. I increases faster than V increases. So therefore, R will decrease as V increases, because we're coming back to this relationship here. As V is going up, I is going up quicker. So R is going to drop because it's all based on that relationship there. And you can see this by, you might want to do this calculation again. You could say, well, at 2 volts, we've got, what's that, about 375. So 0.0375, say, for the current going through there. So we're now looking at taking that 100 up there, 200 divided by 3.75. So you're getting somewhere around the, I don't know, 60 or something like that. Whatever it would be. But it's certainly, if that was 4, you'd have 50 ohms. That's certainly a lot lower than 180 ohms. So yeah, I suppose you could probably answer this just by doing a few sums like this, but it's nicer to see the relationship and show that you understand what's actually happening here in terms of proportional change. I think this goes on to the next. Yeah, it does. Right, a circuit is set up to obtain the IV characteristic shown in the previous graph. Consists of a variable 0 to 6 volt DC power supply connected in series to a 100 ohm resistor and an LED. There's that. Okay, we've just got to finish all this off and then put in suitable meters to complete the circuit. Right, so we need the resistor on the wrong sheet. Here we go. Right, so we got that. So that's our 100 ohm resistor. We know we're going to need an ammeter. We're going to need the voltmeter, and we're putting the voltmeter across the LED. So for our light emitting diode, we're going to have that. We're going to have the arrows to show it's emitting light. Draw all those bits in, and then we're going to want our voltmeter in parallel. Cool, so that's right. I was just double checking for a minute to make sure, because I hadn't actually checked my polarity on the cell. But yeah, we've got plus, minus, plus, minus. So we need the arrow pointing in direction of conventional current, going from plus to minus. So that fits. The arrow is in the big triangle on the LED. Right, so that's that part. Part C, one or more LEDs are often used in places where in the past a filament lamp would have been used. Right, give one example of such a situation. Well, we see them all the time in traffic lights. That seems like a good one to go for, doesn't it? They have notably all changed over recent years. Explain one advantage of using LEDs in place of a filament lamp in the situation you have chosen. Right, well, they're more efficient. That's one of the main things with them. So we've got more efficient. So much the same as we can save energy. So that's the same thing. You could say they got a longer life. That's another thing. They don't blow as often as filament lamps do. Plus you can have loads of them as well, so if one goes it doesn't affect the whole thing. You just lose a dot in your LED array. Lots of things you can say on that. Right, next question. We got two 6-volt torches producing similar light intensities. The light source of one is a filament lamp, the other is a combination of 4 LEDs, and we've got the IV characteristics there. Describe how the resistance of the filament lamp at 6 volts can be determined from its IV characteristic. Right, this is what we've done on the previous bit, isn't it? We've got that R, still on the wrong sheet, R is V divided by I. So you just read those values off of the graph and then calculate the resistance. So you want to say you've got that, and then you can just say read V and I from graph. Right, so state how the IV characteristics show that the filament lamp and the LED do not obey Ohm's law. So, well, for Ohm's law, remember that's saying that we've got a constant resistance. So we're going to have, for Ohm's law, we'd have I is proportional to V, i.e. straight lines. Straight line plot. Neither graph shows this, so you can just say that on the bottom. I won't write it out to save space, but yeah, for Ohm's law we have to have that straight line going through the origin. When at normal brightness, the current in the filament lamp is 0.25 amps at PD of 6 volts. Okay, calculate the charge passing through the filament each second. Wow, okay, that's a bit GCSE of them. So Q equals IT. Well, in 1 second, we're just going to have 0.25 coulombs. Calculate the energy drawn from the battery each second. Right, well, that is, we've got our voltage, which is joules per coulomb. So we've got 6 joules per coulomb. So 6 times a quarter is 1.5 joules every second. The battery is able to keep the lamp lit for 4 hours. Estimate the energy stored in the battery. So we'd have 4 times 60 times 60, that's our number of seconds, times 1.5. Well, what's that going to give us? So we got, well, 6 times 60 times 60, which is, oh my word. Right, so 6 times 3,600 is giving us 18, and then another 3600, so it's going to be 21,600 joules. Right, they weren't too bad numbers in the end. Right, so that's that. Oh, we got a final part to this question. LEDs and the LED torch are connected in pairs across the 6-volt battery and switch, so the potential difference across each of the bulbs is 3 volts. Sorry. Define the term potential difference. So, right, this one's always a fiddly one to define, right? Potential difference, it's the energy transferred. Let's go with that. Energy transferred per unit charge. So really, so what I'm saying there is joules per coulomb is what we're thinking. We know that potential difference is in volts. A volt is a joule per coulomb. But what exactly are we talking about there? We're talking about energy transferred. So that's the joules per unit charge. That's the coulomb. So it just sort of glossed it up a bit. Energy transferred per unit charge moving between 2 points. Between 2 points. Show that the, oh no, we haven't done the next bit. Use figure 1.1 to determine the current through each LED. So we've got a 3 volt, so 3 volts on the LED. We've got 30 milliamps. So that's just reading it straight off of the picture. So it's 30 milliamps at 3 volts. Show that the power drawn from the battery in the LED torch is 0.36 watts. Right, so we've got 3 volts times 0.03, that's our 30 milliamps. So that is the wattage of one LED, and we've got 4 LEDs. So we've got 4 times 0.09, which is 0.36 watts. Sketch a circuit diagram showing how the battery and the 4 LEDs and the switch are connected in the torch. Right, well, they've told us that they're connected in pairs, in parallel. So we know we're going to have LED, 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 LED. Let's put our cell that way round. Leave a space for a switch. We're going to want to put these in that way. A lot of these things to draw out. That way, that way. We need to put arrows on them all. There's a lot to draw in a LED symbol. And then we need the switch, turning it on and off. 4 LEDs, battery, switch. Okay, if we've got a battery, we'll want to put another cell in. If they're going to be particularly picky, then that's probably not what they're that bothered about. Suggest one advantage of using LEDs rather than a filament lamp in a torch. Well, this is the same as we had on the last question. Longer life, more energy efficient, things like that. So yeah, a couple of LED related questions.